Hi all. I welcome you all for this ocean thermal energy harvesting topic. The ocean thermal energy conversion OTEC system is an energy generating technology. This is another way of harvesting energy where we do it by using the ocean waves. So which this OTEC takes the advantage of the difference in temperature between the ocean's shallow warm water and the cold deeper water. So there'll be two different temperatures. One will be the temperature in the shallow water and one in the deep water. So the deeper water will be cold and the shallow will be warm, and this difference in temperature is being utilized to create the energy conversion, or this is done for energy harvesting, which is called as the OTEC, ocean thermal energy conversion. So this uses the heat stored in the warmer surface water to rotate the steam driven turbines. So this turbines which we use here are just because of using the heat energy stored in the warmer surface of water. Likewise, the cold, the deep water, the cold temperature, the cool temperature is pumped to the surface to recondense the steam. Of course, there'll be hot in the warmer surface. To cool them, we use the cooler temperature or the cool temperature that is in the deep water to recondense the steam that drives the turbines. So therefore, the energy is produced from the natural thermal gradient in the seawater layers itself. So this gradient is a self-replenishable source of energy. We don't want any other source of water to condense, and also warmer temperature that is available in the topmost part is being utilized for the thermal energy production and for driving the steam turbines, whereas the one which is in the deep down of the ocean, which is the sea water, is being used to cool, because that is already cool, which is being used to cool down the steam turbines or recondense the steam that has been driving the turbines. So this gradient is a self-replenishable source of energy. So the block diagram here is a simple general overview of the OTEC system. It is a closed loop cycle of OTEC system, which has an evaporator here, and which has this evaporator, condenser, turbine generator, okay, and turbine and generator, and the other components used in the UTC like pumps, grids, which is connected to the power generation, power conditioner system, entry of warm water, entry of cold water to condense it. So all these are just the power cycle of the OTEC, just a simple overview. So we get the warm water, it is sent to the evaporator, then to the turbine, then electric energy is generated, and it has been conditioned, and then it has been condensed using the cold water from the deep down of the seawater. Then it has been pumped and sent back to the again evaporator. So this is a simple closed loop cycle of the OTEC system, nothing but ocean thermal energy conversion system. So mostly, generally, almost 70% of the Earth's surface is covered by oceans, which makes them the world's largest solar collector. So every day, a tremendous amount of solar energy is absorbed by the oceans. Therefore, OT is a vast renewable source with the potential to produce billions of watts of electricity. So generally, OTEC is classed as closed loop cycle as well as so it is also classified as a closed loop as well as thermal principles of closed loop. So here we have the structure and principles of OTEC system. So closed loop was proposed in 1881 by French physicist Dr. Jacques Arsenval. And the closed cycle OTECs use a working fluid with a low boiling point, such as ammonia, to rotate a turbine of heat engine to generate this electricity. So here we have this. So here the closed loop has a working fluid called ammonia, okay, where we have you can just, to rotate a turbine of heat engine to generate the electricity. Warm surface seawater is pumped through the heat exchanger where the low boiling point fluid is vaporized. So to vaporize that, we pass through the heat exchanger and the expanding vapor rotates the turbo generator here. Okay, so this evaporator is used to heat exchanger as a heat exchanger. Then it is passed on to the turbo generator where it is going to rotate the this expanding vapor rotates the turbo generator, and then the cold deep down sea water is used or pumped through another heat exchanger, which condenses the vapor back into a liquid. So it was a vapor here, then it is condensed and made as again, it is then converted back to a liquid, which is then recycled through the system again. So this is how the cycle goes on. So this is the simple structure and principle of the closed loop cycle of the OTEC. So in the closed cycle system, the working fluid is pumped, evaporated, expanded, driven through a low pressure turbine, and then it is condensed. So for the evaporation and condensation, the hot water pipe and the cold water pipe are used for the respective water intakes. As we saw, as we have seen in the OTEC closed loop system, we have two pipes, one for the hot water and the other one for the cold water. At all times, this working fluid remains in a closed system and is continuously circulated like following a Carnot cycle. So this is similar to the standard refrigeration or the air conditioning system. However, it operates in the reverse direction of the Carnot cycle. Okay. Of course, the refrigerators and air conditioners consume electricity to create the temperature difference, whereas this OTEC takes advantage of the already available temperature difference in the seawater to generate the electricity. So high level of energy should be extracted per cycle over temperature limits of 4 to 26 degrees Celsius due to the thermodynamic specifications of this working fluid used in the closed loop configuration. So the working fluid in the closed cycle OTEC system is generally ammonia or propane. Moving on to the thermodynamic principles of closed cycle system. According to the first law of thermodynamics, the energy balance for the working fluid is as shown in the figure, so equation and also in the figure. So QH is the amount of thermal energy absorbed from the hot reservoir, whereas QC is the amount of thermal energy absorbed from the cold reservoir. This will be negative, of course. So TH and TC are the absolute temperatures of the warm and the cold sources, nothing but the cold water. So that is taken into consideration. So this is the schematic. You can see based on the observation, you can understand it. So according to the second law of thermodynamics, the system's efficiency is limited by the efficiency of the Carnot cycle. As shown in figure, the typical Carnot cycle acting as heat engine consists of 4 simple steps. So it's first one is the isothermal expansion of the gas at temperature of TH from A to B. So this is A to B. During this step, the QH quantity of heat is absorbed from the high temperature reservoir. And the second step is from B to C, which is nothing but the isentropic expansion of the gas at entropy SB. And the third step is nothing from C to D, which is the isothermal compression of the gas at the temperature of TC. So during this step, QL, nothing but the quality of heat flows out of the gas to the low temperature reservoir. Then comes the last step, fourth step, which is nothing but from D to A. Here the isentropic compression of the gas at SA happens. So these are the 4 steps that is involved in the like a typical like a Carnot cycle, and acting in the heat engine. This is what is happening in the OTEC conversion. So for an OTEC system, the typical cycle used is the Rankine cycle as shown in the figure. This is the temperature entropy diagram for a Rankine cycle with TC and TH temperatures. So from 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. So there are 4 processes. First is from 1 to 2, which is nothing but the first process is the working liquid is pumped from low to high pressure Since the working fluid is liquid at this process, the pump requires a small amount of input energy. And then the second process is nothing but the high pressure liquid enters a boiler where it is heated at the constant pressure by the warm surface seawater to become dry saturated vapor. And the third process is nothing but the dry saturated vapor expands through a turbine generating power. This process decreases the temperature and the pressure of the vapor. So approximately it's an isentropic expansion. Then comes the vapor, which means 4 to 1. The vapor then it passes through a condenser where it is condensed back to a liquid. So the condensation happens at a constant pressure by cold water to convert this vapor into a liquid. Okay, so these are the four processes of the Rankine cycle. Then comes the components of OTEC system. Here, heat exchangers, evaporators, and condensers are the critical components which are utilized in the OTEC system. So the four components are heat exchanger, evaporator, condenser, and vacuum flash evaporator. First is the heat exchanger. So heat exchanger is used within the closed loop cycle of the OTEC system. This is done to evaporate the working fluid to convert it to a vapor. So heat exchanger can work at two mechanisms. One is counter current exchange and the second one is the parallel exchange. So here is this counter current and this is the parallel heat exchange. Okay. So in the parallel, heat exchange, actually, first of all, in the counter heat exchange here, we have the hot and cold streams flowing in the opposite directions. Yes. So hot stream goes in this direction from left to right, whereas the cold stream moves from right to left. So this as shown in the figure, whereas in the parallel heat exchange, hot and cold streams flow in the same direction, see, from left to right. So determine the temperature driving force for heat transfer in a hot heat exchanger. The LMTD is used. So it is the logarithmic average of the temperature difference between the hot and the cold streams at each end of the exchanger. So this is how the heat exchanger works. Next comes the evaporator. An evaporator is a heat exchanger which vaporizes a substance from its liquid state to the gaseous state. So in the previous component like heat exchanger, it is converting the liquid to a vapor. Now the vapor is converted to from its vaporizes. This actually converts the gaseous state. Okay. So the liquid working the liquid working fluid at the low temperature is fed into a U-shaped tubes absorbing heat from the outside heat source like passing warm seawater, which will turn it into the gas. In an evaporator, the main heat transfer passage is the conduction, not the radiation or the convection happening here. So the conduction heat transfer can be defined as the transfer of thermal energy through the direct molecular interaction within a medium or between mediums in direct physical contact without the flow of the medium material. Next is the condenser. So the condenser is a heat exchanger again, which condenses a substance from its gaseous state into a liquid state as shown in figure. You can see here. So the gas is going to pass through this, whereas we have the cold seawater here. So at last it is converted back into a liquid. So here the gaseous working fluid is fed into the tubes, discharging the heat to the outside cold water where we have the cold seawater. Thus it becomes converts back into the liquid. The operation of the condenser is reverse of the operation of the evaporator, of course. Yeah. And the condenser model is shown here. So in this there is a tank and an observer. The absorber actually, you know, the condenser actually works with the tank and absorber. The absorber has two inlets, one from the turbine, other from the diffuser. And so the working fluid is a mixture of ammonia and seawater. So in this simple model of condenser, the transient performance is a function of temperature, pressure, composition, and mass flow rate of the working fluid. Whereas the vacuum flash evaporator is this way. So the water evaporation rate depends on three factors: the temperature of the water at the air water surface, and the area of the air water surface, and then the H2O molecular concentration of the air, or humidity. So the humidity is the amount of water mass in a particular volume of air, which can be expressed as H equal to m by V, where m is the mass of the water vapor and V is the volume of the vessel. So from the ideal gas law, PV equal to m by m into RT, where this P is the absolute pressure and capital M is the molar mass of the gas, and R is the universal gas constant, and T is the absolute temperature. For a given volume of temperature, humidity is proportional to the air pressure, which means the rate of evaporation can be increased by decreasing the air pressure in the vessel. So this is the operating principle of a vacuum flash evaporator. So as shown in figure, the vacuum pump is used to keep the air pressure in the vessel in a partial vacuum level. So warm sea water is spouted into the vessel and partially turns into the steam. So this is how OTEC works, or closed loop system of OTEC works. OTEC is nothing but ocean thermal energy conversion. The thermal difference in the ocean or the sea water is utilized to convert it to an electricity or generate an electricity. This is how electricity is generated using the thermal energy in the ocean or sea water. Thank you.